Welcome to another session of Everyday Mathematics. Today we move forward to the semifinals of the 2025 MIT Integration B, and our focus today will be on semifinal number 1, where we had 4 problems. The first problem was the definite integral from x equals to 0 to x tending to infinity of the cube root of x over 1 plus x squared. Problem number 2 happened to be another definite integral from x equals to negative pi to x equals to pi of the natural logarithm of 82 plus 2 times open bracket cosine x times square root of 81 minus sine squared x minus sine squared x. Interesting problem. Problem number 3 was the indefinite integral of 3x squared plus 7x minus 5 times open bracket x plus 1 over x close bracket times e to the power x plus 1 over x. Problem number 4 happened to be a definite integral from x equals to 0 to x tending to infinity of x over e to the 2x to the power 2x plus 1. So these are the 4 problems that graced semifinal number 1 of the 2025 MIT Integration B. Today we'll go ahead and solve each problem step by step. Some of our steps will be a little bit longer and protracted, and this is for the reason of edification. We want to just share the thought process behind how to solve such problems. So let's move ahead and solve these problems. So the first thing obviously is it's just a personal preference that I express x as x to the power 1/3, and that's what I went ahead to do. And then one thing I did was to say, okay, let u be equal to the square of x to the power a third, which is just x to the power 2/3. And that means that du dx is equals to 2 over 3 times x to the power negative a third. So 2/3 minus 1, and then the constant becomes the power. Okay? And so when you multiply both sides by 3 over 2, we have 3 over 2 du. That can be used to substitute for x to the power negative a third dx. To create this, what I went ahead to do was I created a phantom x, or by phantom I mean a fake x to the power a third up, and in that way we have created x to the power 2 over 3. And then from this expression here, we can deduce that x is the same as the square root of u to the power 3, which is the same as u to the power 3 over 2. Okay, so now that allows us to come back and substitute u in place of x to the power 2 over 3. And it's easy to know that when x is 0, u will be 0. When x tends to infinity, u would also tend to infinity. So we'll keep the limits as they are. So what we've done here, in place of x to the power 2/3, we have u. In place of x times x to the power negative a third dx, we've put du here. In place of x, we have 2 to the power 3 over 2. And then obviously the constant here, we didn't forget about that. So that means that if we have that, then we can now simplify this portion, u to the power 3 over 2 squared, which is just because we multiply 2 by 3 over 2 becomes 3, so we have u to the power 3. And this is a easy integral to work with. The reason that we went through all the steps to try and come back to this is because it's just cumbersome to use fractions in the powers. So now I do have 1 plus u to the power 3 in the denominator. If we suppose that 1 plus u over 3 is 0, then it means that when u equals to negative 1, this equation holds. So we already have one of the roots, and we can now go ahead and try and do long division to be able to factorize the denominator. So u to the power 3 plus 1 divided by u plus 1, when we multiply by u squared, we get u cubed plus u squared. Subtract that from u cubed plus 1, you get negative u squared plus 1, and then multiply by negative u, that becomes negative u minus u. Subtract from u squared plus 1, negative u squared plus 1, you get u plus 1, and we multiply by 1, we have u plus 1. And so the other factor in the factorization of 1 plus u cubed other than u plus 1 is going to be u squared minus u plus 1. So using that, we can now go ahead and say our u over 1 plus u cubed is the same as u over u plus 1 times u squared minus u plus 1. And so one thing we could do is express this in a partial fraction format. So we have a over u plus 1 plus b u plus c over u squared minus u plus 1. And I mean, as it's customary, the practice when you're dealing with partial fraction, the fraction about the component or the numerator has to be 1 degree less than the denominator. We're putting a, b, and c because we don't know what they are, so we're just going to try and figure out what they are. So when we recombine this fraction with u, a, b, and c as the constants, we'll soon come to an expression that is u over 1 plus u cubed being equal to a plus b times u squared plus b plus c minus a times u plus a plus c all over u plus 1 times u squared minus u plus 1. So looking at this fraction, if this fraction are equivalent, then it means that a plus b should be equal to 0. B plus c minus a must be equal to 1 because there's a hidden 1 here, and a plus c must be equal to 0. So beginning from that, a plus b being equal to 0, b plus c minus a being equal to 1, and a plus c equals to 0, it means that if we assume that a from here, not even assuming, if we deduce from this that a equals to negative c, then it means that a plus b equals to 0, and then here we've combined this c being negative a, so we have negative 2a plus b equals to 1. So when we subtract the second expression from the first one, we get 3a being equal to negative 1, so 0 minus 1 is negative 1, and here a minus negative 2a is 3a, b minus b is 0. So that means that a equals to negative 1 over 3, and then from this expression c would be equal to a third, and what happens is we can now deduce what b is, because from here we have a plus b equals to 0, so it means that b is the negative of 1 over a third, so b equals to a third. Okay. So since our original expression is as shown here, we've deduced that a is negative a third, b is positive a third, and c is positive a third. So we're just going to plug everything in there, and so integration now becomes negative a half, and mark you, we've multiplied 3 over 2 by this negative a third here, so we have negative a half times the integral of 1 over u plus 1 plus 1 over 2. This is positive, the integral the limits remain the same, of u plus 1 over u squared plus u plus 1. And we can express the numerator as the derivative of the denominator, but would have to do some rearrangement, right? So first we have to create a 2 here, and by that we have to put a half in, so half by times a half is a quarter, and then there's this minus u, which when differentiated is -1, so we'll create -1 here, but because we have a positive a half here, so we have to have a 3/4 created here, and this is created because originally here this is plus this is a half, and so because there's a quarter here, we have negative a quarter here, and to go back to this half, we've created a 3/4 times 1 over u squared minus u plus 1. So what that allows us to do now is we can now recombine these two integrals together, because the polynomials, we can just bunch it together. And what we're going to do next is going to actually be very interesting, because here all these fractions have an expression that whose numerator is the derivative of the denominator. And so with that being the case, as shown here, we now can integrate it as not negative for the first one, negative natural log of u plus 1 plus a half the natural logarithm of u squared minus u plus 1. And then we still have our expression here as it is, 3/4 times 1 over u squared minus u plus 1 integrated between x is equal to 0 and x tending to infinity. So this is the same as when we pull the half up, is the same as the square root. So we have square root of u squared minus u plus 1 over u plus 1 using the rules of logarithm, and the limit u is 0 and infinity, half, we've kept it out. And then now we can try to factorize this, and u squared minus u is the same as u minus a half squared minus a quarter, and then plus 1, we've kept plus 1 here. Okay, so we can play around, we can pull u out, because at infinity we don't want to deal with L'Hopital and other things, so we'll just pull u out, and then here obviously negative a quarter plus 1 is 3/4. Going on, what we have, divide numerator by u and denominator by u, so we have 1 minus u plus 1 over u squared over 1 plus u. When u tends to infinity, obviously this tends to 1 and the natural log tends to 0. When u tends to 0, we will with the very first expression, the entire expression also goes to 1, and this entire place goes to 0. But in order to do that, let's first of all sandwich a step so that we cater for the second expression. So when we want to factor out 3 over 4, and since we have a plus operation here, we can just say let u minus a half be equal to the square root of 3 over 2 tangent theta, so that dx d theta is root 3 over 2 sec squared theta, and so du can be substituted off using root 3 over 2 sec squared theta. The limits are interesting, because when u tends to infinity, this entire expression tends to infinity, and tan theta tends to infinity, so theta tends to pi over 2. And then when u tends to 0, 0 minus half, this is negative a half. Negative a half divided by root 3 over 2 becomes negative 1 over root 3, and so tan theta tends to negative root 3, negative 1 over root 3, and so theta would tend to negative pi over 6. So as I said, when u tends to infinity, this will tend to 0, and when u tends to 0, we can multiply by u both the numerator and denominator, we get the initial expression, and we have u squared. So when this tends to 0, we have root of 1 over 1, which will also tend to 1. So natural log of 1 is going to be 0. So 0 minus 0, so this entire expression will be 0. However, we have now introduced the theta expression in the third expression here, or the second from this level. So we have 3 over 4 times the integral from theta equals to pi over 6 to theta equals pi over 2 of 1 over tan squared theta times root 3 over 2 square, which is 3 over 4, which is plus 3 over 4. So we can factor out 3 over 4, and this would cancel out. And then we have here root 3 over 2 pulled out, integral from theta equals to pi over 6 to pi over 2, because tan squared theta plus 1 is the same as sec squared theta, so this would cancel out. So we're now just integrating 1 from pi equals to from negative pi over 6 to pi over 2. So we have root 3 over 2 theta with the limits applied appropriately, and that becomes root 3 over 2 times 4 pi over 6, pi over 2 minus pi over 6 is going to be equals to 4 pi over 6, and then that can be simplified into pi over root 3, and that is the answer. Because what happens is divide by 2, 1, we have 2 here, and then divide by 2, 1, 6 divided by 2 is 3, 3 divided by root 3, so we have root 3 here in the denominator, and that is the answer. This is a very interesting problem. It's a very long integral. I wouldn't really bother to even read through it, but there's a hint after all in all this, and that is the product here. So I'll try to rearrange it. So what we've done here is to rearrange it such that 1 plus 81 is 82, and we have 81 here. So we have cos squared plus sin squared. Cos squared x plus sin squared x is 1 plus 81 plus this product here allows us to see a different expression here, because now this sine squared x interacts with negative 2 sine squared x. So we have cosine squared x plus 2 cosine x times the square root of 81 minus sine squared x plus 81 minus sine squared x. So we see this as the square of this. And so now all of a sudden we see that this was created from squaring cosine x plus the square root of 81 minus sine squared x. So this is where things begin to be very interesting. So we can now say that pulling the 2 out, this is the same as twice, using the rules of logarithm, twice the integral from x equals to negative pi to x equals to pi of natural logarithm of cosine x plus the square root of 81 minus sine squared x. So we can go ahead and now say, okay, let's split this into 2 separate integrals from negative pi to 0, and then from 0 to pi, right? And from here we can now add x plus pi is equals to x, so that this becomes negative cosine x, and because this is a square, this remains the same. So we've done that, and then what happens is we've also when we've added pi to x, this has become 0 here, and this has become pi. And so we have this integral, the sum of these two integrals, yielding, and obviously multiplied by 2, yielding the original integral. So when we combine them together, we can use the rules of logarithm, where now if you are adding them, then it means you're multiplying everything under the log sign. So when we multiply that, it means that now you have a difference of two squares, and that is going to be crucial, because with the difference of two squares, that means that now we have log of negative cosine squared x plus 81 minus sine squared x. So that means is we have twice the natural log of 81 minus open bracket cosine squared x plus sine squared x, and cosine squared x plus sine squared x is 1, so 81 minus 1 is going to be 80, and so that is a constant, right? And we can now just integrate and say, okay, that is the same as twice the natural log of 80, and then x between 0 and pi. So pi minus 0 is pi, so we have 2 pi times natural log of 80, and that's the answer. So the next problem is interesting as well, having the product of 3x squared plus 7x minus 5 and x plus 1 over x times e to the power x plus 1 over x. Very interesting. So one thing that I would do, I would just multiply everything here, so that we do have this expression. I'm just repeating it because I'm trying to figure out what is happening here. I can see for certain that when we differentiate e to the power x plus 1 over x, we have a 1 minus x squared term somewhere. So there is integration, there's a product rule somewhere that I need to figure out. So I could say that, okay, this is the same as the derivative of, because the first term when multiplied by 1 minus x squared is just going to be the same. So 3x cubed plus a x squared plus bx times e to the power x plus 1 over x, and this pulled out times the derivative of e to the power x plus 1 over x. I'm assuming that this is a product rule, and I think it's right. And usually sometimes you just have to guess. And to figure out a plus a and b is what we need to be doing here now. Differentiating that, we have 9x squared plus ax 2ax plus b times e to the power x plus 1 over x, and this is 3x cubed plus 1 over x times x squared plus bx times e to the power x plus 1 times the derivative of x plus 1 over x. So we can now work through everything, and eventually we have 3x cubed plus 9 plus a x squared plus 2a plus b times x minus 3 plus b minus a minus b over x. And what that means is this expression is the same as this expression. So clearly you see that b is 5, and so b minus a is equals to 7. So what that means is that a is equals to negative 2. And then we'll substitute things back to the original expression. Of the product rule, and so we have this, and we can bunch it together into this expression. And so since we're integrating the derivative of a product of these two functions, the integration is an antiderivative, and so our integral is just going to remain as it is, plus the integration constant, obviously. And that's the answer. So this happens to be an interesting problem as well. I look at it, and something allows me to just say, okay, let's divide both the numerator and denominator by e to the power 2x. And so we have the integral from x equals to 0 to x tending to pi of x times e to the power negative 2x over 1 plus e to the power negative 2x. And 1 over 1 plus e to the power negative 2x is an interesting sum, because e to the power negative 2x is less than 1 for the entire interval between 0 and pi. So I could just bring in an arithmetic progression into the equation, but before that I have to introduce a negative here, so that when we have an geometric progression, rather, from k equals to 1 to from k equals to 0 to infinity of ark, we have a as our initial term, r minus 1. And if we're beginning from 0 here, and there is no a, it also means that we could just have 1 over r minus 1. But if r is less than 1, then we have 1 over 1 minus r. And that's the same thing we have here. Anyway, so we're going to pull that here, and keeping the numerator as it is, we have negative 1 to the power k, this negative here, times e to the power negative 2kx. And then now we combine all the x's, because we can pull that in. So we have negative 1 to the power k, integrated between x equals 0 to x into infinity, times x to the power e to the power 2 times k plus 1x. So we can pull the integral sign out, because integrating the sum of things is the same as the sum of the integral of things. That's just straightforward. We don't need to prove anything there. Let's use integration by parts to attack this. When you have a product of v and a derivative of function u, this is what you get. You have a product of u and v minus the integral of u times the derivative of v. So using that, we have our big summation here, negative 1 to the power k. And so we have x then obviously we have u being this, so the integral of u is going to be e to the power negative 2k plus 1 x over 2k plus 1. And it's easy to see here that if this negative is taken into consideration, this comes into the denominator, and using L'Hopital rule, derivative of numerator and denominator in the event both the numerator and denominator tend to infinity, means that we're left with 1 over this, and so the entire expression goes to 0. Okay, so we have this limit tends to 0, this limit tends to 0. When x tends to 0, obviously this x goes to 0 and the entire thing collapses to 0 since this stays to 1. So that taken into consideration, we have a derivative of x and leaves us with this negative here, and so this negative and negative here interact to become 1 because we have things here. So derivative of x leaves us with only e to the power negative 2 times k plus 1 times x over 2 times k plus 1. We can pull out the 2k plus 1 here, 1 plus 2k plus 1 times 1, and then when we integrate things we get negative e to the power 2 times k plus 1 times x over 2k plus 1. And so that means that eventually now we do have 1 over 2k plus 1, 2k times 1, our limit as x tends to infinity of this. As x tends to infinity, the numerator tends to 0. And here limit as x tends to 0, this tends to negative 1. So 0 minus minus 1 becomes 1 over 2k plus 1. So this 1 over 2k plus 1 times 1 over 2k plus 1 here, it becomes 1 over 4 times k plus 1 squared. So we have an interesting problem here. So we have a scenario where we can pull a quarter out, and we have negative 1k over k plus 1 squared, and that means it's the same as a quarter. When k equals to 1, when k equals to 0 here, that means that we have positive 1, and then here is 1 over 1 squared. And then when k equals to 1, we have this becomes negative 1, and k plus 1, and 1 plus 1 becomes 2 squared. And so we have 1 minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared. So this term, when this is even, is when we have a negative sign here. And this allows us to see that we need to exploit what is called the Bezel problem. Okay, so we've separated odd terms, even terms. The Bezel problem says that if you have a summation of 1 over k squared from k equals to 1 to infinity, that adds up to pi squared over 6. We won't really bother to prove it because that's supposed to be in your bag of tricks or part of what you need to be knowing. So to find out what the odd terms and the even terms add up to, first of all, we can now recreate our sum as it is, and then we separate the odd and even terms as shown here, and then we can pull 2 squared out from the even terms, such that we're still left with 1 over 2 squared is 1 over 4, so we still left 1 over 1 squared, 1 over 2 squared. So this in itself is still the Bezel problem summation. So we can plug pi squared over 6 here, so that the odd terms plus a quarter times pi over 6 is equal to pi over 6. So the even terms definitely add up to pi squared over 24. So what that means is that the odd terms is pi squared over 6 minus pi squared over 24, where when I found out that the odd terms add up to 3 pi squared over 24, because 24 divided by 6 is 4 pi squared minus pi squared, we have 3 pi squared. So what does that mean? It means that that's the same as pi squared over 8, and the even terms is the same as the total sum minus the odd terms. So pi over 6 minus pi squared over 8, which is the same as pi squared over 24. So since our problem led us to a quarter times the odd terms minus even terms, so we have pi squared over 8 minus pi squared over 24, which is a quarter times pi squared, actually 2 pi squared over 24, because 24 divided by 8 is 3, so times pi squared, we have 3 pi squared minus pi squared, we have 2 pi squared. So divide by 2 here, we have 2, divide by 2 here, we have 1, and then so 2 times 24 is just going to be equal to pi squared over 48, and that's the final answer.